Hi everybody, thank you for coming to watch this Canyon Academy physics video. In this physics 112 concept video, we are going to be talking about the concepts from week 10, which are interference, Hyugen's principle, and Young's double slit experiment. And so for the majority of these three concepts here are sort of interrelated in that you need to understand interference in order to have a better understanding of Hyugen's principle and Young's double slit experiment. So that's what we're going to talk about first, is the interference. And interference is just defined as, quite simply, two or more waves that are at the same place at the same time. And so you may or may not recall that in physics 111 we talked about how sound waves are capable of interfering with each other. And so for this instance we're going to be talking about light. And in order for interference to happen with light, the waves that are interfering with each other, they must be coherent. And that means that they have the same wavelength and the same phase relationship. And by phase relationship, we were just talking about where the waves crest and where they trough at. And so what's also important to note is that these waves, they must be one color. They must be monochromatic in order for interference to occur because they have to have the same wavelength. And we know that if there's more than one color involved, then these colors must have different wavelengths. So as you can see in the diagram below, I'm sure most of you have heard of constructive and destructive interference before, but we're just going to talk about when these can occur. And pure constructive interference can occur when identical waves are exactly in phase. So the amplitudes of these wavelengths are just simply added together. If you look at this diagram, then so if you look here, we can see that the amplitudes of the first and the second wavelengths are just added together, so that on the second, in conclusion, we have a longer amplitude here. And so this is exactly opposite of what happens during destructive interference. Although these amplitudes may add together, because they're shifted exactly 1/2 wavelength apart, it'll just result in a line that's straight, and then all the light will completely destructively interfere. And so with that being said, what we're going to talk about next is the Hyugen's principle. And Hyugen's principle is basically talking about how every wave has a wavefront, and that wavefront is divided into secondary wavelets. And so these wavefronts are the source for these secondary wavelets to occur, and that's how a wave can spread, basically. So like it's written here, the wavelets propagate in all directions with equal speed. So as this wave, if you imagine each of these black lines as a wave. So let's say you drop a rock. You drop a rock into a pond. Waves are going to spread in all directions from where you drop that rock, and they're going to travel at equal speeds. And so this first line right here, it can be defined as a wavefront. So that's the front of the wave. And as this wavefront is propagating in this direction, we can see that in order to spread, these wavefronts have their own wavelets. And so these wavelets are basically the start of a new wave. So this is how the waves are capable of propagating. And so now if we consider a barrier, so we're going to consider this as a barrier up here. And this is where it's relevant for Young's double slit experiment. As the wave is propagating in this direction and comes into contact with this barrier, where there's only one opening here, we're going to have this front wavelet be this front wavelet is going to be the way that this wave can travel through that barrier. And then we have basically the same thing as what we started with this rock, where the wavelets are propagating new wave fronts. And so what's important to note here is that if you consider sound now, so if you go around the corner from your friend and your friend is trying to talk to you, you can still hear your friend talking to you even though you're around the corner. And that's because sound is capable of bending around barriers. And so in the same way, light is capable of bending around this barrier here. And so we're going to talk about that a little bit more with Young's double slit experiment. But just so you know that Hyugen's principle can just simply be summarized as the edge of a wavefront creating a series of circular waves. And the amount of bending is more extreme for a small opening. So what we're going to talk about next is Young's double slit experiment. And this was an extraordinary experiment that provided a lot of evidence for the wave nature of light. So I'm sure you're going to learn that light, there's a sort of theory that the light can exist as both a particle and as a wave. That's the wave-particle duality nature of light. And so what Young decided to do was he set up a diffraction grating where we have two slits. As you can see in this diagram here, we have two slits for light to pass through. And so this light is a single wavelength light, and it's sent through the pair of vertical slits through which it is diffracted onto this screen. Here's the screen. I'm sorry. So here's the screen right here. And then the light is coming in, and it's a single wavelength light, monochromatic, and then you can see how this light is going to travel and diffract on this screen. So on the screen, we're going to have regions where the light is constructively interfering and destructively interfering. So we're going to have a pattern of vertical lines, as it's written here, vertical lines that are both dark and light. So we're going to have regions that are dark, regions that are light, dark, light. And then so on this screen, the 2, 1, 0, 1, 2 correspond to the maximum. So this is where, this is just, the central maximum is just the central order, the 0 order, and then this is the first order, then the second order. So this is basically describing how the light appears on the screen. And so there's basically two mathematical relationships that we can identify from this experiment. And the first is that if you consider this first small triangle over here, and if this is theta right here, so we can observe that the distance d between the two slits multiplied by the sine of theta of this triangle that we have formed here is equal to the m, which corresponds to the maximum, times the wavelength. So this is basically, we know that sine is equal to, sine of angle theta is equal to opposite over hypotenuse. So the hypotenuse in this instance is the distance d, and what's opposite of theta is wavelength. So that's how we can multiply d over to the other side. So that's how we get d sine of theta is equal to wavelength. And this wavelength is dependent upon what maximum you have. So how far away from the 0 order are you considering? And so the second mathematical operation that we can identify involves L, which is the distance from the slit to the screen, and X, which is the distance between maximums. And so by using tangent of angle theta here, we can see how tangent is opposite is equal to opposite over adjacent. And so that would be X over L. So that's how we derive this second mathematical operation. And so this is basically what you need to know for Young's double slit experiment for solving different problems with that. And then you should, what's especially important here to know is that it provides evidence for the wave nature of light because because we can see how on the screen the light can form vertical lines of both dark regions and light regions. So if light was only a particle, then the light would simply, let me get yellow here, then light would simply only continue straight forward through this slit and leave regions of light on the screen. However, because these waves are interfering with each other, we have regions that are both dark and light, meaning that the light has to be in its wave form. So this is the concepts for week 10, And if you have any questions, go ahead and leave them in the comments.